So we'll talk about our next lab, which is lab 8. Now in this lab, we'll talk about something a little bit different, which is called interrupts. Now interrupt is a signal that is given to a microprocessor by the user, like us. Okay. Now microprocessor jumps to a special subroutine called interrupt service request once it gets the interrupt. Now to understand the interrupt better, I give an example always. For an example, let's say we are having this class right now, and suddenly we have our fire alarm ringing. Okay. Now what do? No matter what we are doing here right now, we'll stop it, and then we'll follow some procedure, right? Because that is so important and so prioritized that we have to stop everything and we have to follow some procedure, okay? And then once we are done with that procedure, we'll return back to the class and then we'll resume, right? The interrupt is exactly like the procedure that I just explained, gave you as an example. Because what happens is, as you can guess, that microprocessor is probably doing some other operation, microprocessor is busy with something else, even the computer that you're using in front of you, probably your microprocessor is right now busy with some software operation, okay? But if you give a signal to the microprocessor, meaning like an interrupt, microprocessor jump onto your interrupt and serve a request. Now, what might be a good example of the interrupt for your computer? Every keystroke that you make, the mouse click that you make, all of these are interrupt. Why? Think about the microprocessor. See, you might be like copying like 2 big files, so you might be doing some other operation like watching a video lecture or watching something else or running some other software. At any point in time, if you press the keyboard, any key, right, it displays the key or it does something based on your key, right? How it happens. Think about the microprocessor. No matter how fast your microprocessor is, no matter what microprocessor it is, as of today, any microprocessor given any time can do at max one operation. Any microprocessor at max. And that means whatever it was doing, since it responded to your keyboard stroke or to your mouse click, it actually stopped, served you, went back. No matter what it was doing, because this is an interrupt. Okay. Now, even if you probably have, I'm not sure how, probably you already know it. Just as a quick example, when you see the you are probably, let's say, copying like 4 different files from 4 different places. Every file is like 20 gig, okay? You might be very happy, wow, my microprocessor is doing so much for me. But if you have just one microprocessor in your machine, because most of the machines right now have like more than one, but if you have just one, your microprocessor is actually serving one request at any given time. There is no way microprocessor can serve more than one. Because as you can have seen so far, microprocessor actually follow the instructions, just nothing else. But when you are doing such big operations, okay, in your screen you'll be watching, oh, it's actually all the 4s are running at the same time. Your microprocessor is doing a little bit of trick. What it does is it's actually jump back and forth between these processes and keeps doing work, but it jumps and switches back and forth so quick you will never realize it's actually giving the break and it skips things. And and you probably know it, because when you are copying one single file and then when you are copying like 20 different files, you'll see that how things get slow, because your microprocessor is actually serving one process in one time, but it's actually keep jumping back and forth. And even at that point, if you press some key, it will jump to your request, display something or do something, and then go back, because the keystroke is considered an interrupt. Similarly, in our microprocessor, like the microprocessor that we work with in our lab, microprocessor by the Motorola, we can also give a similar signal like an interrupt to our microprocessor. Okay. Now what it does, once microprocessor receives the interrupt for us, it actually runs as subroutine. Anything actually is a subroutine, okay? Subroutine is what? Is a function, right? You know, in high-level language, you're more familiar with the word function, right? But the subroutine is still pretty much the same thing. That means whenever you were asking, you know, something special, microprocessor is actually running a subroutine for you. Now, in our case, you might be wondering, what is this subroutine and what is this subroutine? This subroutine is called interrupt service routine. Even if the name is a little bit interesting and different, it is still a subroutine, okay? Now, and the next question, what is this subroutine and what is this subroutine? This is actually a subroutine written by you. This is really interesting and powerful. That means you are the one who is writing a special subroutine, and then any given time you are giving a signal, meaning an interrupt to the microprocessor, and microprocessor stops everything, jump onto use subroutine, runs it, goes back to the regular. So there is also some other interesting part. I think you can guess that whenever microprocessor stops whatever it was doing and jump onto use service, whatever microprocessor is doing with, you know, it might be working with accumulator A, it might be working with something else. All those accumulators, all the content of those accumulators are actually reserved in somewhere in the memory location, so that once it goes back to the previous work, I'm saying previous process, it can resume from the point it stopped. But it still save all of those accumulator and all of the contents, so that once you start working with the same accumulators, those data do not get lost. You see what I'm saying? A lot of exciting thing. Now, in our case, if we want to understand and look at them, you know, look at this a little bit more closely, this is exactly what happens. At the first step, we give a signal to the microprocessor by a hardware pin called interrupt service pin, in short IRQ. Okay. Step 2, that means this is a hardware signal. Okay. Now remember, this can be software signal as well, but at this point in this lab, we're actually talking about the hardware one. Okay. So microprocessor responds by pausing the execution of its main program. As I said, whatever the program it was running, microprocessor saves the status of the content of all the registers, and then, because you know it has to resume at some point, right? And then microprocessor jumps to a special subroutine that you have written, which is called interrupt service routine. Okay. As I said, there are two different types of subroutine. I'm saying the interrupts, software and hardware. Okay. Now, in this specific lab, we'll just talk about this highlighted one, interrupt request. This is a special type of hardware interrupt. That means this is given by hardware. Okay. So again, interrupt request is just like a pin in an IC. Okay. Think about the microprocessor. At the end of the day, microprocessor is nothing but an IC, right? It's not like your NAND gate, or it's not like your inverter, like that small. It will be a little bit bigger IC, but at the end of the day, it's just like an IC, and it has the pin numbers. Okay, so the interrupt service pin is really like a physical pin in your microprocessor. Okay, but how can you reach this pin? Because in our case, as you can guess, you can reach to the microprocessor directly and connect to the pin, right? How can you reach it? Very easily, because in your case, that pin is also connected to the black slot. In the black slot, you will find a pin called XIRQ pin. That is the pin which you need to look at, and then But just by look at the XIRQ pin, can you guess that how can you give the signal? Because think about this black slot. Every single black slot here, if you want to connect, or if you can connect, you'll be connecting it with what? Either with ground or VCC or any other pin, right? But since this is a digital circuit at the end, it will be either 1 or 0. But just by looking at these, as you can see, there is a bar at the top of this, right? Do you see the bar?
Oh, yeah.
That actually means what? That means that this pin is an active low pin. That means this gets activated by 0, not by 1. You know what I'm saying? So this means if you connect that pin to the ground, then you actually are giving the signal to the microprocessor. You know what I'm saying? Now, how do you give a signal? You actually give a signal just touching it one time, very quick. But if you keep it connected, let's say you just run a wire and you connect it to the ground forever, then what happens is you are constantly giving the microprocessor to the signal. So what microprocessor will actually run the interrupt service request, meaning the subroutine, again and again and again and again. So that means forever. It will keep running it. So it will look like that microprocessor is running an infinite loop. And then same subroutine will be run again and again and again. Okay? We'll talk about this very soon. Now, to understand the interrupt service routine, meaning the subroutine, as I said, the subroutine that you write, the first question is, how do we write the interrupt subroutine? There might be some special procedure, right? Now, we actually write only one line of code in a predefined memory locations called interrupt vectors. Now remember, in your computer, in our computer, in our memory locations, we have some reserved, predefined memory locations. So there are some specific locations. I'll talk about those locations. But do you see this interesting thing? You actually can write only one line. That means only 2 bytes. Now, can you really write a subroutine in 2 bytes? It's almost impossible, right? To write a subroutine in 2 bytes. So what do you exactly do then? This is interesting, that instead of actually writing the subroutine, what you do is you actually call the subroutine in that place. So this is exactly what you do. See, you just write something like this: jump and then a name of a subroutine. Now remember, XIRQ service is the name of a subroutine, and this subroutine, this name is given by us. So that means you can change this name, you can give whatever name you want, right? But all you are doing is using that 2 byte. Remember, in 2 byte you can write one line like this, right? Because this line is a jump or branch instruction which has an object code of length 2 bytes, right? What are the 2 bytes? The first byte is an opcode, second byte is a relative address, right? So basically, you will be just saying, oh, jump to that subroutine. Now, what is actually the subroutine? You are not writing the subroutine. Instead, you are calling the subroutine because you just have 2 bytes. So this is a little bit tricky, because what you are doing is, in that place, because that is a reserved 2 byte location for writing the interrupt request, you are just calling the subroutine, but the real subroutine is actually written in your program starting from D000. But you know, as long as you are just calling that subroutine, no matter where you are writing the subroutine, that subroutine will be executed. Do you see what I'm saying? That's really interesting because you just have 2 bytes reserved. Now, what do you write the code of subroutine? Now again, as I said, we just write it in our program. Remember, in all of our program, we start from where? D000, and then we write a bunch of code and to do something. We can write the subroutine there, okay? But make sure we always call it in a specific location, okay? Now, to understand what we are doing in the lab 8, this is what we'll do. An interrupt is applied. How do you apply it? By momentarily touching the momentarily connecting the XIRQ pin in the black slot, meaning the P1 connector, and the ground bus, meaning connecting the ground, right? Now, once you touch it, what happens? Definitely a subroutine is executed, right? You have written the subroutine in your program, okay, which actually is already written for you. We have written it, you just have to execute it. So what happens is your board is already connected to a 7-segment display. It's connected to a 7-segment display, and then 7-segment display will actually display a digit between 0 to 9. It will actually start from 9, okay? And then if you touch it again, it will display the next digit, like 8. So it will actually keep decreasing every time. That's how actually we have written the subroutine. We'll show you the subroutine, okay? So that means it will show you 9 first, and then if you touch it again, it will show 8. If you touch it again, 7. If you touch it again, it will show you 6. So basically what it is doing is every time it is calling the same subroutine. But the subroutine is interesting. This is how we actually wrote the subroutine. We actually said show 9, and then we change the number. Next time it shows 8. And then we again change the number so that the next time it shows 7. Okay. Now if you keep that wire connected, then your 7-segment display will keep changing the number like this: 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, again 9, 8, 7. So it will keep changing, it will keep running. So you might be wondering, it might look like that somebody is running a loop, but there is actually no loop. What is happening is microprocessor is keep calling the same subroutine again and again and again. So every time it calls it, it actually displays a number, which is the next lower number. Okay, so it will look like you are running a loop, but there is no loop. Okay. Now there is a very small circuit there. All you have to do is connect the port B with the 7-segment display, and that's it. So if you see these wires here, instead of the regular wire, we actually use a register in all of these lines, a 220-volt register. Why we use the register? So that we can control the current to the 7-segment display. Okay. If you don't use the register, this may not be a big deal. All might happen is you'll see a much brighter light, because there will be a lot of current sent to the 7-segment display, and there is a chance that you might your 7-segment display may get burned, or so we just use a register. So what we exactly write in the code, let me show you what exactly write in the code. Remember I said we have 2 different bytes reserved for the interrupt service request, right? Those bytes are FFF4 and FFF5. How do I know these 2 bytes? This is actually defined by the Motorola. So we'll show you where exactly we got these. But these are the 2 bytes defined by them. So you can change them, saying these are predefined. Okay? Now, what we do is in our program, somewhere at the bottom, we write like this: ORG XJXIRQ. Now remember, XIRQ is like a label. Okay? This label means FFF4. That means all we are saying is start from FFF4, meaning the following line, next line will be starting from FFF4. This is exactly the interrupt service request. Remember, in that 2 byte, what do we write? We just write a 1 single jump instruction, right? And this is our jump instruction, jump XIRQ service. So we still have not written the subroutine. We are just calling the subroutine from there, right? And we are done. But the real subroutine will be located in a different place. But before that, let me show you how do I know that the vector address, this is called interrupt vectors, okay? These addresses, like reserved addresses, where we write the interrupt request, meaning we call the subroutine. So where do we get it? We actually got it from a chart like this. This is a chart given by Motorola, okay? This is predefined. So if you look at this chart, do you see that in one of the row I actually marked, I did an arrow. So as you can see, the interrupt source is XIRQ pin. So for this pin, the reserved address is FFF4 and FFF5. These 2 bytes. So this is pretty much defined. So I actually got it from this chart. This is actually provided in the Motorola handbook. We'll talk about this handbook a lot in next semester. Okay? Next semester we'll talk about, we'll work with this handbook a lot. I'm saying, you have not seen this handbook yet, but we probably gave a couple of references to this handbook. Now, how do you write this subroutine? Because we are just talking about the subroutine, right? We just call the subroutine, but we still have not seen where is the subroutine. The subroutine is written under your regular program, starting from D000. So this is actually the subroutine. So we already have written the subroutine for you, and we already written it in the lab 8 procedure. So you don't have to modify anything. All you have to do is just understand what you are exactly doing, so that anytime you see any question in your bonus part, remember in the bonus part you see the question from the lab, right? In case you see some questioning from the bonus part, in the bonus part, you at least can answer the question. Okay. Now, so let me quickly go over this so that you understand exactly what we are doing. Okay. At the very beginning, at the very end, actually, we have a digit table. Do you all see this table? Table means we actually put some information here for different. So you see here, this is a table. Table means, again, very simple thing. It starts with something like a label. See, digits is like a label, right? And then it's saying the digits means C0. So it's actually first byte is C0, second byte is 79. Next is A4, 30, 99, and the next is 12, 82, 78, 80, and 18. Now, what are these bytes? Interestingly, these bytes are the information for different digits. So for an example, C0 is the information for the digit 0. How it is the information for digit 0? Remember in the last class, we have shown you how to highlight F. And for F, we actually have written a hex number. Remember? There was a hex number we have written for F. And then we send that hex number to the port B. This is pretty similar. This is exactly the same thing. So think about the C0. If you write C0 in decimal, in binary, what is the C0? It's actually 1100. That's you see, right? And then 0000. So this is you C0 in binary, right? Now think about all the segments that you have in your 7-segment display. You have a decimal point, right? And then you have A, B, C, D, E, F, G. Now, your 7-segment display is also like an active low device. That means that all the segments that is connected to a 0 input will be turned on. Everything else will be turned off. Now think about digit 0. If you have to turn on digit 0, what happens? You will be actually turning on every single segment except the middle one, right? That will be 0, right? Now that middle one is actually your A, which you are turning off. You see the A is turned off, right? Because A is 1. And decimal point is also turned off. There is a decimal point at the bottom right. That is also turned off. You see the decimal point is also turned off. So every single other segment is turned on because those are 0. So that's how the C0 is actually an information for your digit 0. Same is true for 79, because if you decode 79 just like in this way, you'll see that the 79 is actually the information for digit 1. Similarly, A4 is the information for digit 2. 30 is the information for digit 3. The same is true all the way to the end, because 18 is the information for digit 9. You see what I'm saying? It's pretty much in the same way, okay? Now, this is how we actually start. At the very beginning, we load. See what we are loading? We are just loading. See how we wrote it. We started with the pound sign, right? Pound digits plus 9. What exactly it means? This means load the last address of your digit table. Now what is the last address? See, the digit table is actually here, right? This is your digit table. Okay? The last address is actually the address of 18. Now we are not loading 18. We are actually loading the address of 18. Be careful, okay? How it is an address of 18? Because every time, remember we talked about this in the class in our I think last lectures. So whenever you use a label and then you just said FCB, anytime you mention digit, it actually loads the address of the digit. So basically you are loading the address of 18 into index register X, and then if you look at this, we are just saving that into a variable, and again that's the same thing, the address of 18. So that address of 18 is again loaded back to X, and then we are doing an indexed address instruction here in here LDAA 0x. Now what exactly we are doing here? We are loading this. We are just saying LDAA, I'm saying after all of these lines, we are actually saying LDAA digits, right? Now what this digits means, that's the address of digit, right? I should actually say digit plus 9, because at this point the index register X says digit plus 9, right? So basically what we are saying is LDAA digit plus 9. Now think about this. This is, at this point, is like an extended instruction, right? Because digit plus 9 is an address, right? What will be loaded into your accumulator A? Your accumulator A will be loaded by 18. Because you never load the address, right? Think about the index addressing. What do? If you look at if you get any index addressing, you go to the map and load the data from the map, right? It's the same thing. So this is the address. Digit plus 9 is an address, which is an address of 18. So in the real accumulator, 18 will be loaded. And then all you are doing is, look at this, STAA port B. That means you are storing 18 to your port B. And the port B is connected to 7-segment display, right? So all you are doing is sending 18 to your port B, meaning sending 18 to your 7-segment display so that it displays 0. Okay. Now, in the next two lines, we are calling a subroutine DQUR. Now, this is a subroutine written by us. This is located in the header file. Remember the cpt.h or cent.h header file that we included at the very top, at the very beginning? That header file is always there in the lab computers, right? Now, this subroutine is a subroutine which actually adds a delay of a quarter second. So we actually called it twice because we wanted to have a delay of half second. Now, why we need the delay? The reason we did the delay because we are displaying 9, right? And if the subroutine is called again, we'll show you how it will display 8. Now, between 9 and 8, we want to put a delay so that you can see the change. If we don't put this delay, your computer will run this subroutine so quick, so fast, you'll not even see the changes. You'll see the 7-segment display, and all the segments will be just like blinking. You'll never know what digit is displayed. It's so quick. So we wanted to have a delay, and then do you see that we are reducing the index register X? What that means? Remember, the index register X has the base address, right? What is the base address? The base address is actually the address of 18, right? We decrement it by 1. That means right now the base address is the address of 80. So the base address is the address of 80. Now what is 80 again? 80 is the information for digit 8, right? I'm saying if you decode, you'll know this is just digit 8. Now, what is next? We are just checking in the next line, we're checking whether we arrived at the beginning of the table. This actually is the beginning of the table, because think about the beginning. The beginning of the table is actually digits, right? So before that, what do you have? Digits minus 1. Now, if we arrive beginning of the table, what do? You want to go back to the 9 again, right? Because you want to display 9 again next time. So if this, comparison is true, you do not go to this branch. This branch doesn't make, and then you actually go to the next line where you again load the address of digit 9, right? Meaning address of 18, $18. Otherwise, you go to the N. That means, this is really interesting. What it does is, every time you call this subroutine, let's say at the beginning, it actually displays 9, and then it set the pointer to 8. So that next time you call it, it displays 8, and then it set the pointer to 7. So that next time when you call it, it displays 7, and then set the pointer to 6. Because every time it's actually decrementing the counter by 1. That means you are changing the base address so that next time it is called your accumulator A, and then accumulator A will be loaded by the address of the next previous number. Okay? But if you keep it connected, it will keep running and keep displaying the previous digit until it reaches 9. I'm saying until it reaches 0. Because when it reaches 0, it goes back to the 9 because of this CPX digit -1. Okay? Again, this subroutine is already written for you in lab 8, so you actually don't have to modify anything. Only thing is you need to understand a little bit so that you understand the bonus part in the test in case you see any question from lab 8. All right, so we'll do a little bit extra, not for the lab, but to understand a little bit more and how we exactly did this. Now, can we modify this subroutine so that it displays the digit in an increasing order? Right now, your subroutine is actually displaying the digits in a decreasing order, right? So if you want to change it, what exactly you will change? Look at a couple of lines. Look at there are only 4 lines that I actually changed, and I highlighted those 4 lines as bold. What exactly I did? Look at this. At the very beginning I said, load the first address of the digit. See, this is the first address, right? This is the first address of the digit. I loaded that into X. This is the address of what? Address of 0. Because since this is an increasing order, I want to start from 0, right? So this is actually the address of 0. And then that address is loaded into index register X. And then here, you are actually loading the real content of that address. What is the content? C0, right? Which is the information for 0. That is loaded into A, and that data is also sent to the port B, meaning sent to the 7-segment display. And then you are adding to delay, and then look at this. Instead of decrementing the address, the base address, you are incrementing, right? So that next time it will load the address of 1. And that way, your accumulator A will be loaded by the address of digit information, meaning by the content of that address, which is the information for digit 1, right? So, and then, instead of checking whether you reached at the beginning of the table, this time you'll be actually checking whether you reached at the end of the table, right? That's exactly what we did. We checked whether we reached at the end of the table. If we did, we do not make this branch. We go back here. I'm saying we go here, and then we load the beginning again. So that means anytime you display 9, the next digit you want to display 0, right? So you'll go back to the beginning of the table. So these are the only 4 lines that we are actually changing here so that we can display in an increasing order. We don't actually need it for the lab, but we still want to understand it just to make sure in case we see any question from this lab in our bonus question part, okay? So that we understand how we can modify this subroutine. What are the lines we exactly need to change so that we can do, we can display it in a different fashion, okay? But it's still doing the same thing, sending some data to the 7-segment display, but in a different order. Any question? All right, so I'll give you the procedure for lab 8 so that you can start working on this lab. And I'll stop my presentation here.